Our next topic is magnetic flux. The magnetic flux is similar to the electric flux. Flux we always indicate with phi. If you remember, electric flux we indicate with phi E. Since this is magnetic flux, we indicate with phi B. Okay, measured in Tesla meter square, also measured in Weber. So that phi B is nothing but how much magnetic field. So here is my B, okay, and here is the area of a rectangle. Okay, it could be a circle, rectangle, square, doesn't matter. So here that phi B equal to magnetic field passing through the unit area BA cos theta, where theta is angle between B and tangent to the area. Okay. My apology, we call that as normal to the area. Okay, so normal to the area is in this direction. So here is the normal, this is the normal to the area. Now what is the angle between B and normal to the area? In this case it is 0, so we'll see the maximum magnetic flux. Now here is a magnetic field B. Now I place my paper or rectangle like this. So this is flowing in, say, x and y plane. Now I placed this in x and z plane. Okay, my area. Now in this case, what is phi B? In this case, phi B equal to 0. So magnetic flux is similar to the electric flux. Phi B equal to BA cos theta, Tesla meter square or Weber. Now I'm going to talk about Faraday's law. So Faraday's law. So according to Faraday's law, as long as there is rate of change of magnetic field, an EMF induced across that conductor. An EMF induced across the conductor. Okay, so here induced EMF always indicate with E equal to rate of change of magnetic field, induced EMF across the conductor. Now I'm going to change this little bit. Actually Faraday's did. I'm going to rewrite again Faraday's law. As long as there is rate of change of, instead of magnetic field, I'm going to say, or he said, magnetic flux. Okay, and EMF induced across a, instead of one conductor, I'm going to say this as a coil. So as long as there is rate of change of magnetic flux and EMF induced across that coil, that E equal to d phi by dt. Now say if there are n number of turns, n equal to number of turns. Okay, so for example, here is a magnetic field B. Okay, here it is constant, magnitude is not changing. So here is B. Now I have a coil. Here is a coil. Okay, now this coil has n number of turns. Okay, this coil has n number of turns. And now if I'm moving this coil in one direction, so now this coil has area A, right? So magnetic flux is nothing but B times A cos theta. Here cos theta equal to 0, so you will end up with maximum magnetic flux. Now if I move this conductor in one direction, what happened? There is always the magnetic flux is changing. Okay, so whenever we are moving this, there is a rate of change of magnetic field. So as long as either conductor is moving in a magnetic field or magnetic field is changing, or the magnitude of the magnetic field is changing, then there is an EMF induces across that conductor or across that loop. So there are two ways to produce EMF or induce EMF. One is conductor has to move in a constant magnetic field. Okay, so the first one is either conductor has to move in a constant magnetic field. That's one way to induce an EMF. Another way is magnetic field has to change. As long as there is rate of change of magnetic field, there will be an induced EMF. Now after Faraday, Lenz came across, he just modified a little bit. So according to Lenz's law, so here is Lenz's law, he mentioned that induced EMF E always oppose the rate of change of magnetic flux. So that's what this negative indicates. So according to Lenz's law, so induced EMF always, so the induced EMF always oppose the rate of change of magnetic flux. That's what this negative indicates. So that indicates that I'm going to draw a coil here. Okay, here is a coil. Assume that there is a current passing through this. That current is AC current. What is AC current? I'll talk about it. So if current is passing through this, so it's an alternating current. Alternating current we always indicate with small letter, and DC current we always indicate with capital letter. Now alternating current, this current is changing. So whenever current is changing, there is always, this is nothing but an inductor solenoid. If you remember, there is always lots of magnetic field inside this coil. Okay, now this is a conductor and there is lots of magnetic field inside this, and that magnetic field is changing. For sure, according to Faraday's law, there is an EMF induces across this. Now according to Lenz's law, he's saying that induced EMF is oppose the rate of change of magnetic field. So if the magnetic field is increasing, you will see this is plus and that's minus. When it is decreasing, this is going to be plus and this is going to be minus. Okay, so E equal to, in this case, n d phi by dt. N is number of turns. That's what the Lenz's law indicates.